Hello guys, welcome back to ptet.chemistry channel. So this is a continuation of these topical MCQs on A-level questions. These are multiple choice questions on mole calculations and stoichiometry. So for instance, this is a 5-question series. So in this question 36, we are asked to find the mass of the gas that will occupy a volume of this much at 25 degrees Celsius and 1 atmospheric pressure. So they told you that 1 mole of this gas occupies this much volume. So this is the molar volume of the gas at 25 degrees Celsius and 1 atmospheric pressure, which is what we associate it with room temperature and pressure usually. So that's 24 dm cubed per mole of any gas at room temperature and pressure. Alright, so the first thing that I would be thinking about really is to convert this volume of 3 dm cube into mole, because it's a lot easier to understand in terms of how many mole of gases we are looking for. All right, so if I convert that, then there will be the mole of gas will be 3 dm cube divided by 24 dm cube per mole, and if you follow the unit carefully, you will see the dm cube and dm cube cancel, and that will give you 1/8, which is 0.125 mole of gas present. So now my job really is to go through the options and convert the mass related to the molecular mass of each of these species and find which one corresponds to 0.125 mole. So in terms of molecular masses, so I can work out the molecular masses of oxygen is 16 times 2, so that's 32. So the mole of O2 is going to be 3.2 divided by 32. I can tell you that's not the answer because it will not give you 0.125. This is 1/10, so that is just 0.1. Just checking on my calculator. So this is not what we are looking for. A is not the answer. How about B? So I have the molar mass of N2, which is 14.0 times 2. By right, I should have used 16.0 because that is your periodic table for A levels. So 28.0, just to be consistent with the decimal place as shown. So how much mass we have? 5.6 gram. So there's 5.6 over 28.0. That is 0.2 mole, and that is not 0.125, so that is not what we're looking for. If I continue this thing here, so I should just continue it side by side so that it's easier to follow. So the molar mass of SO2 will be 32.0 times 1 plus 16.0 times 2, and they give me 64.0. So the mole of SO2 would be 8.0 divided by 64.0, and I could see that straight away is 1/8, so that is exactly what we're looking for. So it is this much mass of SO2 gas that actually corresponds to the same mole as this 3 dm cube of gas at room temperature and pressure. By the time I get my answer, I don't really need to check the last one, but you could if you want to. The molar mass of CO2 and then the 11 gram divided by the molar mass of CO2, you will not get 0.125. Alright, so the answer there is C, and we'll move on to the next question. In this next question, so the old type of A-level questions, they'll remind you to use data booklet when it's related to that question. I think the new type of A-level multiple choice questions, they no longer tell you to refer to the data booklet. It's simply up to you. Do you need the data booklet or not? It's really up to you to decide whether you actually need it or not. So taking a look at the periodic table, so we have a coin that has a mass of 10.0 gram, of which nickel makes up 20% of this 10.0 gram. We are asked to find how many nickel atoms are in the coin. So first of all, you probably should work out the mass of nickel in the coin. So the mass of nickel is 20%, so it's 20 out of 100 times 10.0 gram. So there's 2.0 gram. Your calculator will show you as 2 gram, but I know better because this mass was given to 1 decimal place. I could give it to 1 decimal place, or I could give it to 3 significant figure based on how appropriate was the data that I have been provided with. Not a big problem in paper 1, but it becomes a big problem when you don't know what is appropriate number of significant figure, and these are very clearly stated in the syllabus for mole calculation and stoichiometry topic, that you have to be careful of what is appropriate and not, especially in practical, especially in theory, especially in your experimental design and planning and analysis. So the next bit is, once I find out how much mass of nickel, then I should work out how many mole of nickel atoms I have. Once I know mole of nickel, then I can start to figure out how many atoms I have by relationship to Avogadro constant. So N there refer to number of mole of nickel. That's going to be the mass over the molecular mass. So instead of MR, by right I should use a relative atomic mass because nickel is an element. So straight to the periodic table, nickel has a relative atomic mass of 58.7. I really don't want to, I can see it's not a very nice number, so I just keep it as such. Accordingly, then I will have the number of nickel atoms will be the mole of nickel, how many mole I have, multiplied by Avogadro constant, because Avogadro constant is basically how many atoms in 1 mole. So if I know how many mole, then multiply by Avogadro constant, that will give me 2.0 divided by 58.7 times 6.02 times 10 to the power of 23. The Avogadro constant is given for free in your data booklet, for free in front of the data booklet. So I've gotten the answer as 2.05 times 10 to the 22, which is option A there. Question 38. So this is quite a direct question. We're just looking for molecular formula. So molecular formula has a definition. The definition is, it tells you the actual number of atoms in one single molecule. So this thing, they say camphor has the same percentage by mass of hydrogen and oxygen. So we need to work out the molecular mass for each of these based on the molecular formula. So there are 10 carbon there, so 10 times 12.0. Oops. And then you have to add 6 times 1.0. So perhaps I can show you one, and then you can just press your calculator very, very carefully, because it's important that you don't press the wrong number. So 6 hydrogen times 1.0 plus 6 oxygen times 16.0. Okay. So 10 times 12.0 plus 6 times 1.0 plus 6 times 16. So there's 222. That is for option A there. So I should check the percentage by mass of hydrogen. Okay. So how in the world do I check this? Well, let's have a look at the hydrogen first. So 6 hydrogen, so it's 6 times 1.0 divided by the molecular mass. Okay, times 100%. So 6 times 1.0 divided by 222 times 100. They give me 2.70%. Percentage by mass of oxygen. So there's 6 oxygen. I can tell you that will not, without even calculating it, that will not be equal to 2.70%, because, well, just have a look. The denominator is the same. The denominator is 222, but the numerator 6 times 1.0 is not the same as 6 times 16.0. So realistically speaking, we are looking at this because these and these are the same denominator. So for the rest of my calculations, if the MR is the same, which they will be the same for each of these, I don't really need to calculate the MR for each of these. There will be a waste of my time. I just need to compare how many hydrogen, how many oxygen. I need to total them up. I need the numerator. So that is the key factor here. By doing one, I can see what I need to do to compare the trend. So for B, C10H et al., doesn't matter what the molecular mass is, because the denominator, the one at the bottom, will be the same when I compare the percentage by mass of hydrogen or oxygen, which they are asking us to compare because they have the same percentage by mass there. So just talking about the numerator, so hydrogen, I have 8 times 1.0 is 8.0, and then oxygen, well, 16.0 times 1, or perhaps I can say 1 oxygen times 16.0 is 16.0, does not equal. If they do not equal, then it doesn't follow the requirement where they have the same percentage by mass of hydrogen and oxygen. Okay, so up next, I can almost see that is the answer there, because 16 times 1.0 is 16, and then 1 times 16.0 is 16. All right, so let me just show you C10H16O, C10H16O. So for the hydrogen, again, if you want the percentage by mass, the denominator will be the same. Whether we're calculating for hydrogen or oxygen, the denominator will be the molecular mass, which again doesn't matter because they'll be the same. So I just compare the numerator, the number on top. For hydrogen, I have 16 of them. Each one is 1.0, so 16.0. For oxygen, I have 1 oxygen. Each one is 16.0. So total is the same. If the total is the same for the numerator, for the top part of the value, and the denominator is the same, then of course the percentage by mass will be the same. So we have gotten the answer as C there. And of course you can see D very quickly, that is wrong, because that is 10 times 1.0 is 10.0, 16.0 times 2 is 32.0. Obviously they are not equal, therefore D can also not be the answer. But I already gotten the answer at C. I don't need to check D if I really don't want to. Question 39 is about balancing chemical equations. So what they have told you is this equation can be balanced using oxidation number. So by right, I should really have classified this question as part of redox chemistry, because in the redox topic in AS chemistry, candidates are, or students are expected to be able to balance chemical equations, redox equations in particular, by using changes in oxidation number. All right. You could of course get it from scratch by comparing the ratio here. All right, so for example, you have 2N to give you iodine, 2N plus 2N plus P, that refers to iodine, is equal to M. So a few algebra expression could help you to balance this. Of course, you could also use changes in oxidation number. All right, so what's the relationship between N and P here? If you haven't done this before, you can obviously balance it from scratch, as I mentioned. So N here refers to the number of mole of iodine. All right, so if you look at number of mole of iodine atoms, on the left you have M times 1, because there's 1 iodine and there's M multiple of it. So M times 1 on the left is equal to 2 times N plus P times 1. So it's 2 times P times 1, so M is equal to 2N plus P, and then you need an expression for P as well. P relates the hydrogen and P relates the oxygen also. Okay, so this might be a long windy method using algebra, but I'll just show you first before I show you the changes in oxidation number method. So the number of hydrogen, M times 1, is equal to, so we're looking at hydrogen, so P times 1 plus 2 times Q. So M is equal to P plus 2Q. The other one will be the number of oxygen atoms. You look at M times 1 on the left hand side, and then on the right you have 3 times P and then Q times 1. Alright, so 3P plus Q, M is equal to 3P plus Q. So all of this refers to M, and we just really have to work out the simultaneous equations. So 1, 2, and 3. What can I say? So if I have 1 is equal to 2, that means 2N plus P. This is equal to M, this is equal to M, so I can equal this and this. 2N plus P is equal to P plus 2Q. The P and the P cancel, because you move the P to the other side, it become P minus P. So 2N is equal to 2Q, N is equal to Q. What else can I say? if I equal these two, that is not going to be helpful to me at all. I can probably get another relationship. If I double, so 2 times 3 give me 2m equal to 6p plus 2q. So if I have then sub in m is equal to p plus 2q. Oops, sorry, m. So basically sub in equation 2, which is m equal to p plus 2q. So 2 times p plus 2q is equal to 6p plus 2q. So you can see this method is really getting really tedious. That's because, what am I doing here? This doesn't look good at all, does it? Oh, it's not so bad actually. So 4q minus 2q equal to 6p minus 2p. 2q is equal to 4p. Q is equal to 2p. So we have gotten n is equal to q. We have gotten q is equal to 2p. So therefore, n is equal to 2p. So we're looking for n is equal to 2p. N is equal to 2p, so A is wrong. N is equal to 2p, so 2 times 1 is correct. N is equal to 2p, okay, so that one is wrong. N is equal to 2p, so you have B or D. And how do we know which one is correct? Again, you might really have to balance it from scratch, and I think I must have done something wrong here. What else can I say? If n equal to 2, then I have 2i2, and then p is equal to 1, then q is equal to 2p, q equal to 2 times 1, that is 2, and then m, well, this was all m, right? M equal to 2n plus p, so 2 times 2 is 4, plus 1 is 5. So if I have 5 hydrogen, there will be 1 hydrogen plus 4 hydrogen is 5. Iodine would be 5 iodine, so 2 times 2 is 4, plus 1 is 5. Oxygen, there's 5, so 3 times 1 is 3, plus 2 is 5. So really we are looking at B. We are looking at B because there's something in the question that actually tell you the answer. They are simple whole number in their lowest ratio. Lowest ratio, 2:4 is not the lowest ratio because you could simplify this to become 2:1 in their lowest ratio. So that's why B was the answer. Alright, so I was confused for the wrong reason. Now, I need to show you also how to balance this oxidation number, how to balance these changes in oxidation number, and how we're going to use it to balance this equation. Alright, so if I just cut that, and I'll make some space down at the bottom here. Okay, so using changes in oxidation number. So that was like traditional methods, algebra, balancing from scratch, whichever one you like to call it. Okay, so we know the iodine here, the hydrogen is +1, the oxygen is -2, therefore the iodine is +1 because +1 + 1 -2, overall oxidation state of the compound is 0. This is iodine 0. This is iodine +5 because this is oxygen -2. There's 3 of them, so there's -6. This is +1. +1 plus iodine -6 equal to 0. So the iodine is +5. Alright, so we're going to look at the changes in oxidation number for the iodine. The iodine go from +1 to 0, there is a -1. The iodine go from +1 to +5, that is a +4. The changes in oxidation number must balance out. This is a result of you gaining 1 electron. This is a result of you losing 4 electrons. So the lowest common multiple, primary school mathematics, 1 and 4. The lowest common multiple is going to be 4. Meaning to say, I need to multiply this by 1 and I need to multiply this by 4. Alright? So it has to be a changes of 4. So there has to be 4 in front. So if m is equal to 4, alright, and this has to be multiplied by 1, so P must be 1. And what else? What else can I say? If there is 4, if there is 1, but that is impossible because it has to be whole number, right? This one. So because of the minus 1, and this is I2, so I must be looking at this being 2. If this is 2, so this is a classic disproportionation. So this species, 4 of the I plus 1 goes to here, but you need one more. You need one more of the HIO because 1 of the iodine plus 1 goes to here. Because there's only one species that gets both reduced as well as oxidized. All right, reduction is decrease in oxidation number. Oxidation is increase in oxidation number. So the plus 4 here, 4 of them, is 4 of these is involved in this process. So it's multiplied by 4. But I need to add one more because one of it is involved in the other process. So altogether, I need 5 of these. So M is equal to 5. And therefore, here it balanced now. 2 times 2 is 4 plus 1 iodine. All right. The Q can be balanced out once the changes in oxidation number is balanced. That's why we get N equal to 2 and P equal to 1. N equal to 2 and P equal to 1. And this is 5 because of the need to balance out the changes in oxidation number. You actually have this species both undergoing reduction and also oxidation. This is something you will learn as disproportionation reaction. This is under AS redox or as electrochemistry. Definitely by the time you have learned group 17 chemistry, which is the same as group 7 chemistry in O-level or IGCSE, you will have heard of this term by then. Alright, so I hope that was useful to some extent. So 2 different methods. If you couldn't really do that methods at the moment, you could have done the traditional method where you just put in the value and see whether you get a balance or not. The other method is of course using oxidation number. Changes in oxidation number must be balanced out. We do lowest common multiple, LCM. This is the last question of this 5 question series. So I spent quite a bit of time on the question 39 by showing you both methods. But anyway, so I hope that was useful. So now we have aluminium burned in oxygen, and this product is reacted with this much hydrochloric acid. So how much acid is required for the complete reaction? So the first reaction, reaction 1, is aluminium burning in oxygen. It will give you an oxide, Al3 plus, O2 minus. I hope you can see that you need 2 of the Al3 plus and 3 of the O2 minus for the charges to be balanced out. So the ionic compound that you form overall has no charge. Balancing the equation, 2 aluminium here would mean 2 aluminium here. 3 oxygen here would mean 3 over 2 oxygen here. Some students, some teachers really don't like fractions. You could have multiplied the whole thing by 2. You could have gotten 4Al, 3O2, and 2Al2O3. But if you're in A levels, you would know that fractions are actually more convenient to balance chemical equations. In fact, I like fractions a lot more than whole numbers. So it's really up to you which one you like. Okay. Reaction 2. We react this product. This product is actually Al2O3. React it with HCl. Later on, in fact, back in O-level or IGCSE extended chemistry, you will have learned something called amphoteric oxide. Al2O3 is amphoteric oxide because it reacts with both acid and also base, something you will revisit in period 3 chemistry eventually. So when it reacts with an acid, it's going to undergo neutralization. So it will behave like a basic oxide. Even though it's amphoteric oxide, it can react with both acid and bases. It's going to give you a salt and also water. Okay, so 2 aluminium there give you 2 AlCO3, 6 Cl there would mean 6 HCl, 6 hydrogen would mean 3 times 2 H2O. So 3 times 2 hydrogen, therefore you need 3 H2O. The oxygen, there's 3 of them, it balances out. Okay, so the question really is, what is the minimum volume of acid that will be required for complete reaction? So this is the mole of aluminium. You will know the mole of this. If you know the mole of this, then you know how much acid will be required to react. And if you know the concentration of this acid, you can work out the volume of the acid. So the important thing really is compare mole ratio. The aluminium give you the Al2O3. The Al2O3 reacts with HCl. So from our first equation, 2 aluminium give us 1 Al2O3. From our second reaction, 1 Al2O3 reacts with 6 HCl. 1 Al2O3 reacts with 6 HCl. When we want to combine the two equations together, you must make sure that the common ratio is equal. Here they are equal. If they are not equal, you need to take lowest common multiple of primary school mathematics, or at least it was when I did school. But here they are equal, so the LCM is just 1, so I can just bring down the 1. Alright, so here it means 2 aluminium will go on to react with 6 HCl. So the mole of HCl over the mole of aluminium is going to be 6:2, which of course you can simplify later on. Alright, so I've just decided to put mole of HCl on top. If you gotten them the other way around, it's not a problem, because this is about bookkeeping. In my other topical playlist on mole calculation and stoichiometry, you will see that it's never a problem. It's just that you must label what is what, so that you never get confused. If you gotten the other way around, then your ratio will be 2/6, because the 2 is for the aluminium, the 6 is for the HCl. This is from the balance equation, balance stoichiometry equation. Alright, and then on the right hand side is the actual amount that reacts. So actual amount of aluminium that reacts is 0.02 mole. So put the 0.02 mole there. And then the actual mole of acid will be the volume of acid times the concentration, which is 2 mole per dm cube. So 2 mole per dm cube multiplied by the volume. The volume is all in cm cube. So if the volume is in, so that volume was in cm cube, so we will have volume in cm cube times 10 to the minus 3, or volume divided by 1000. Okay, so simplifying all that, the volume is going to be 6/2. I will bring that up and I will bring that down. So it's 0.02 on top, and then 2.00 times 10 to the minus 3 at the bottom. This volume is in cm cube. Press that onto a calculator, and I get 30 cm cube. Of course, being appropriate would mean to 3 significant figure, so something like 30.0 cm cube would have been appropriate. So that's the end of this 5 question series on calculations, mole calculation, stoichiometry. Do subscribe to my channel if you like my videos. Click the button on the bottom right, and share the channel widely with all your friends, your chat group, your study groups, and various other groups, various other people who might be doing O-level, IGCSE, or A-level chemistry. There are separate topical playlists for the O-level and IGCSE students. And yeah, I hope the videos have been useful, and follow me at ptet.chemistry on all the popular social media platforms. Thank you for watching, and I'll see you in the next video.